is an interesting SMO junior problem, and the first thing I'm going to do to get started here is just write down the prime factorization of 187. So 187, it's easy to establish that 187 is equal to 11 times 17. Both of those are prime numbers. So 187 is equal to 11 times 17. And the larger the primes, I think the easier these problems typically are. Maybe, I'm not sure if that's really true. Okay, so that's the truth. 11 times 17 without a calculator is 187. Okay, now also another very useful truth right here is that if you have a prime dividing a product, any prime number, this is a well-known result from number theory, any prime number that divides a product has to divide one of the factors of that product. That's not true of a composite number, so that's a special result that we appeal to here regarding primes. Okay, so if P divides a product of the two integers A, B, that implies that P divides A or P divides B. And the proof's kind of fun, and it's again, it's not true for a composite number. There's plenty of counterexamples to show that. So that implies that P divides A or P divides B. And again, we're talking about integers here. Of course, this is the domain of number theory. Now, the reason why I'm taking the time to write that down is that's exactly what makes this particular problem tick. If you'll notice, we have the product of 4 consecutive natural numbers, and we're also given that that product is a multiple of 187. But notice that if you apply this result sort of inductively to this, we can establish that 11 and 17 must divide one of the factors n plus 1, n plus 2, n plus 3. And that's the answer to the y question. One way to see that is to think of A as the product n times n plus 1, and B as the product n plus 2 quantity times n plus 3 quantity. And then you just apply it again. So it implies sort of in an inductive fashion. Okay, so we know that to be true because of this number theory result. And so we go ahead and give a name to the factor that is divisible by 17, and we give a name to the factor that is divisible by 11, x and y respectively. Now notice that from n to n plus 3, there's a distance of 3. None of the integers in this group of 4 factors, n plus 1, n plus 2, n plus 3, can be further than 3 from each other, and that's established easily. n plus 3 minus n is just 3, right? So we get this absolute value statement. Now, we don't necessarily need to use absolute value here since all the numbers we're dealing with are negative, and we're taking x to be the factor divisible by 17, which is bigger than 11, but it's still good practice to use the absolute value. Now, notice that when you get x is equal to 17, this inequality here, this difference, absolute value inequality, implies that y could possibly be 14, 15, 16. Notice I skipped 17. We're already dealing with 17 right here, 18, 19, and 20. Now notice right here that y, this list of values of y that would be the only possible values of y if x were equal to 17, none of these y's are divisible by 11. So I'll write down 11 does not divide y. We use the long vertical bar to connote divides, and we put a slash through it to negate that relation. So 11 does not divide y. Okay, like that. So we go to our next multiple of 17. 17 is a multiple of itself, but 34 is also a multiple of 17. That means 17 divides 34. Now notice if you apply this inequality to this number x, you get an other list of numbers. And notice that we actually get a multiple of 11 right here. 11 does divide 33. Okay, that's good news for us because that's exactly what we're looking for here. 11 and 17 are the divisors of 187, right? So 11 divides 33. And that's a terminate condition, so to speak. And so what we can establish right here, we're looking for the smallest n that satisfies this condition up here. So we can see that that string of numbers would have to end with 33 and 34 to ensure the minimality of n. So I'm going to write 33 times 34. And these numbers by themselves are divisible by 187, right? Just by construction. The product 33 times 34 is already divisible by 187, or is a multiple of 187. Those are equivalent notions, all right? But notice those would have to be the last two numbers in this product of four consecutive natural numbers. And so what we get right here is 32 is our next one. Okay? And you see, this is kind of like we just have to tack this on to satisfy the conditions. 33 times 34, I repeat, is already divisible by 187, but that's not the full conditions of the problem. And so here we have it, folks. Product of four consecutive integers, and 31 would be the smallest natural number that meets the condition of the problem statement. Okay? That is the answer, folks. There's no need to multiply all that out. We already know that this part alone, and again, I'll write this down just for the sake of clarity. 33 is 3 times 11, right? So there's your 11. There's the presence of the precious factor 11, all right? And also, I'll do that parenthetically. Not really necessary, but just to enhance legibility. Now, right here, this 34 is 2 times 17, right? And again, perhaps this is overkill, but you already got the condition satisfied with the last two factors of the product, all right? But again, they didn't ask for the product of two integers, two consecutive integers. They asked for the product of 1, 2, 3, 4 consecutive integers. Anyway, 31's final answer. I hope you enjoyed.